In this section, we're going to talk about different ways to record solution concentration. The first way is molarity, extremely important in the laboratory. We'll use it all the time, and it's a good skill to learn. If you're ever working in a lab, that's what you're going to be using. If you'll notice right at the top, it's abbreviated by a capital M, and some of you have already noticed that on a lot of solutions that we use in class. When they're at the table, you'll notice a big M on it. So you're going to learn what that means and how to make it up. First off, you'll notice that molarity is the number of moles of solute in 1 liter of solution. And in our lab, we're going to have water as our solvent. So it's moles per liter. And this is just an example of 0.5 moles of NaOH in 1 liter. And so we abbreviate that as 0.5 molarity NaOH, which means, again, 0.5 moles in 1 liter. Another way to do solution concentration is molality. This is the number of moles of solute in 1 kilogram of solvent. You'll also notice that molality is abbreviated with a little m. Some of you have been abbreviating moles with a little m, and if you notice, you can't do that really because little m means molality, which means moles of solute in kilograms of solvent. So an example is if you have so many moles of NaOH, and if this was in 2 kilograms of water, you'd have to divide it out and you'd end up with a solution of molal of NaOH. So how is this different than molarity? Because it sounds very much alike. So let's look at how it would be created. So I want you to draw this on a sheet of paper so that you can see how this works. So molarity, you need a volumetric, which are very accurate, and they can be different sizes depending on how much you make up, but in this case I'm going to do it in a liter because that makes the math very easy. But in class, you'll never be making up a liter because we just don't have enough for everybody to do that. So first of all, you'd add a little bit of water on the bottom, and you'd calculate out how much solute you would need in grams. And you would add that in there. Now, the only reason why we put some water in the bottom is so that it mixes better and it doesn't get stuck on the bottom. The next step is you would bring it up exactly to the mark, and you need to be exact, up to 1 liter with water. So if you were only making 50 mils, you would bring it up to the 50 mil mark, but in this case 1 liter. Then you'd mix and you'd be done. Now molality, you can do it in the same container if you want to. So you'll put in your solute, the amount that you calculated, and you're going to add 1 kilogram of water. If you remember, 1 liter equals 1 kilogram of water because 1 gram equals 1 mil. That's the density of water. So we're able to use a liter container to pour this in. But if you notice, there's already stuff in the bottom. So when we add this, there might end up being a little bit more solution than at the line because we're not measuring volume here, we're measuring weights. So our final volume can be more than 1 liter. Molarity is used a lot in the lab. Like I said, this is an excellent skill to learn. We're going to be using the math a lot with this. Molality is used for number ratios. It's important in a number of things, but the one you'll want the most is it's for the ice cream lab because it will tell us our freezing point depression and our boiling point elevation. So it tells us the changes in temperature. Another way to do concentration is mole fractions. And you've done this math before. It's just part over the whole. So if you notice, here's the part, which is the sodium hydroxide, and then you'll have, in this case, sodium hydroxide and water on the bottom. You can also make a percent out of it. So again, it's the part over the whole and then multiplied by 100. And you're all pretty familiar with that. So 5 grams of NaOH and then 5 grams, and in this case we have 2 kilograms of water And so we multiply that by 100, and then you get this percent. We can also talk about parts per million and parts per billion. These are extremely small amounts. We would never measure this out in class, but we need to be able to know what it stands for. So this is like 1 gram in 1 times 10 to the 6th gram. It's a very small amount, but it's very important when you're talking about pollution or different nutrients in the water. We measure this a lot of times, like nitrates, nitrites, ammonium in the water, and you really don't want more than 2-3 parts per million before you end up with some problems. But some things you want in the water, and like dissolved oxygen. So you need nutrients, but you don't want too much. And they record these all in parts per million and parts per billion. So let's look at the worksheet here. First of all, molarity is a capital M, that's the way to abbreviate it, and it's moles per liter. So if you're given a 2 molar solution, this means you have 2 moles solute in 1 liter of water. You need to be able to say that if you see the 2 molar, what it exactly means, because we'll be using that a lot in the math. So a 4.5 molar solution would mean that we had 4.5 moles in 1 liter. Let's do some math on this. If you notice, we have 2 moles of sodium chloride, and we put this in 4 liters. So all we have to do is divide 2 moles by 4 liters, and we get 0.5 molar solution of NaCl. The big thing to remember is that that means 0.5 moles of NaCl in 1 liter solution. Be sure to note what you're given, because you can't use mils, you have to convert that to liters. Nor can you use grams, so you have to be able to convert the grams into moles. Just a reminder, sulfuric acid is H2SO4, so you can look up the formula weight. Another one you'll need is phosphoric acid, that's H3PO4. Another problem that may come up is that if you're given so many liters of a solution and you know the molarity of it, you'll want to calculate out how many moles you have. So we can do a T-chart on this. The first thing to remember is that a 2 molar solution means 2 moles over 1 liter. This easily goes into a T-chart. So we start out with our given, 0.5 liters, and then on the bottom we're going to need liters, and we'll need moles on the top, which conveniently is what a 2 molar solution means. So we have 2 moles in 1 liter. Calculate it out, and you find out you have 1 mole of NaCl. Don't forget to convert your mils to liters when you do the next problems. Finally, this type of problem is what you're going to be doing a lot in the lab to be able to make up a solution. You want to make up 100 mils, and you want to make up a 0.5 molar solution. You'll want to calculate how many moles this is, but more important, you'll want to calculate how many grams this is, because we don't measure moles on a balance, we measure grams. So again, we start. Remember that 0.5 molar means 0.5 moles in 1 liter. We'll use this in the T-chart. So we start out with our 100 mils, but we can't use mils in this equation, so we convert it right away to liters. And then we need to get to moles, just like on the other problems. So we know moles on the top, liters on the bottom. We remember that 0.5 moles, molarity means 0.5 moles in 1 liter. Now at this point, this gives us moles of NaCl. We can calculate it out. We end up with 0.05 moles. Our final step is we need to go to grams. So I can continue on with the T-chart. And using the periodic table, I know that 1 mole equals 58.5 grams of NaCl. and I multiply that final part out and I get 2.925 grams.